Module A1, Objective 2. Be able to define the following terms: matter, ion, element, molecule, compound, isotope. These terms are introduced in Chapter 2, and the definitions can be found in your glossary. Matter is anything that takes up space and has mass. It can either be living or non-living. The study of matter is important to physiology and anatomy because chemical characteristics determine physiology or determine the function of an organism. This hierarchy begins at the molecular level with chemistry, proceeds through the cellular level, and on into higher levels of organization of the organism, from cells to tissues to organs to organ systems to the organism. So understanding the basis of function and how chemicals react and how matter works is going to help you to understand anatomy and physiology. There are 3 states of matter: solid, liquid, and gas. Solid is of constant volume and shape. If you think of a desk or a glass, those are both solid type matter. If you think about the liquid in the glass, that volume remains the same, but it can change shape. If you tip the glass to one side or the other, the liquid is going to move and change shape. And in the gaseous form, both volume and shape can change. The second term is the term ion. Ion refers to atoms or molecules that lose or gain electrons. The structure of an atom, remember there's protons in the nucleus of the atom, and there are electrons in an electron cloud outside of the nucleus. Protons are positively charged, electrons are negatively charged. In the normal state of an element, electrons and protons are typically going to be in balance. They're going to be equal, so the number of protons in the nucleus will be the same as the number of electrons in the electron cloud. But in some cases, because those electrons live in these shells, if I have a nucleus that contains protons and neutrons, and outside that nucleus I have electrons, the first shell, the maximum number of electrons is 2. In the second shell, the maximum number of electrons is 8. So if I have 2 electrons in this inner shell, then that shell is satisfied. That's the most it can hold. And I'm going to have 8 electrons out here in the outer shell, and it's satisfied. But what happens if I have a third shell, and that has only 1 electron? That shell is not satisfied. It would need 7 more electrons to be satisfied. The chances of it getting 7 electrons is very low. So what has a tendency to happen is it will lose that outer shell electron. It will come off. And now what we would have had inside were 11 protons. I didn't put that in there before, but 11 protons, and we had 11 electrons outside. But it loses that outer shell electron. And when it loses that outer shell electron, it now has 10 electrons. So don't read, just ignore that for right now. So it had 10 electrons, 11 protons with a positive charge. So now we have a net positive charge. And this represents sodium, Na+. And that's how sodium looks in ionized form. So here we have sodium again. So you see 2 electrons in the first shell, 8 electrons in the second shell, and that lonely electron out there in the outer shell. To become satisfied, it's less reactive actually. It keeps these 8 and loses this 1 electron. So that electron goes away, and we now have sodium as an ion, and that's called a cation. Cation. If you remember, think that right there, think T, and T for positive charge. So cations have a positive charge. Some of the other cations that are important are potassium, K+, calcium, K2+, and magnesium, Mg+. And then you'll see those throughout the semester. You also have the case where sometimes an element has a nearly full outer shell. Look at that chlorine atom. It has 1, 2, let's count them, 1, 2, 3, 4, 5, 6, 7 electrons. It's missing 1 electron. So what it has a tendency to do is pick up electrons. Let's say here's an electron. So let's say here we have this electron. Out here, it's a little big, sorry. And it's going to get picked up by chlorine. It's got a negative charge. And when that happens, chlorine ends up displaying that electron having that negative charge. It's satisfied, less reactive when it has that electron out there. So it is now called an anion. If you think about what the term an means against, or it means negative. Okay, so if you're anti something, then you are against that. So remember, an means negative. Cation, put that T in there, means positive. Anion is a negative ion. Now what happens with sodium and chlorine is that because they have those opposite charges, because sodium is positively charged and chlorine is negatively charged, they have a tendency to attract each other. And that is called an ionic bond. So up here we have this term ionic, and we're going to learn about ionic bonds in the next unit. The sodium crystal is held together by ionic bonds. And these types of bonds are not a very strong bond. They're more of an attraction. If you remember opposites, do what? Opposites attract. Opposites attract. So the positive and the negative have an attraction towards each other. And this crystal form is not considered a molecule, but it is a compound, and this is what you would find in your salt shaker, unless of course you're using a salt substitute. An element is our next term. An element is a pure substance. Remember that term, pure substance, that contains atoms of only one kind. So we'll look more at molecules and compounds, and that hopefully will become more evident to you. Elements have a particular atomic number. And the atomic number can be found on the periodic table. You can go to the internet and find a copy of the periodic table and look up the atomic numbers of some of the elements that are important to living things. I believe that information is also available in your textbook. The atomic numbers is basically the number of protons found inside the nucleus. And again, usually number of protons is going to equal the number of electrons, but that number of electrons can change. If you take away a proton or add a proton to an element, you are changing the element. It will no longer be that element. If you remember from the previous objective, we looked at hydrogen and helium. Hydrogen has an atomic number of 1. And helium has an atomic number of 2. Helium has 2 protons in its nucleus. Hydrogen has 1 proton in its nucleus. Helium has 2 electrons in its electron cloud. Hydrogen has only 1. If hydrogen here with 1 proton in its nucleus and that shell having only one electron, it needs another electron to satisfy its outer shell. So that electron needs to, it either needs to gain an electron or lose an electron. And what has a tendency to happen with this particular element is that electron actually is lost oftentimes. So hydrogen ends up being what many people call a naked proton, and it has a positive charge. So it's a cation. Other elements that are important to living things are oxygen, which has an atomic symbol of O, carbon, which has an atomic symbol of C, hydrogen, atomic symbol H, nitrogen, atomic symbol N, calcium, atomic symbol Ca, phosphorus, atomic symbol P, potassium, atomic symbol K, sodium, atomic symbol Na, chlorine, atomic symbol Cl, magnesium, atomic symbol Mg, sulfur, atomic symbol S, iron, atomic symbol Pb, and iodine, atomic symbol I. Those atomic symbols you should learn and recognize because those are ones that are going to be in the various chemicals that we find in living things. These are the most abundant. They make up the large majority of living organisms. The next slide is showing what are called trace elements. They make up a very small percentage of your body. However, they are essential to life. Without them, we would not be living. They are silicon, fluorine, copper, manganese, zinc, selenium, cobalt, molybdenum, cadmium, chromium, tin, aluminum, boron, and vanadium. I'm not as concerned that you recognize the chemical symbols for these. You will see them. You should be able to look them up on a periodic table and find them. But know that these trace elements and recognize the names of these trace elements as things that are essential for life. The next term is molecules. A molecule is two or more atoms joined by a covalent bond. A covalent bond is a particular type of bond. If you look at that name, covalent, and you remember that the shells of electrons are called valence shells. Co meaning together, co-workers, you work together. So covalence has to do with sharing. So in a covalent bond, you have the sharing of electrons. Another term is the term compound. Some people get compound and molecule a little bit mixed up. A compound is a pure chemical substance made of two or more atoms of different elements. The key there is different elements. Carbon dioxide, listed here, is showing a molecule of carbon dioxide, which is a compound. If you notice, here you have 2 electrons, and here another 2 electrons. Over here we have 2 more electrons, and here's 2 electrons. Let me tell you something about carbon. Carbon is very unique, and there's a whole branch of chemistry based off of the carbon atom. Carbon has an atomic number of 6, which means that it has 6 protons. We figure out its number of neutrons by its mass. Its average atomic mass is 12, so it has 6 neutrons with neutral charge or no charge in the nucleus. And it has 6 electrons. The first shell would have 2, and the second shell would have 4. And the way I draw these usually is by separating those 4 out, because there actually are 4 different places where you can have, they're called orbitals in shells. There are 4 different orbitals, and you'll get into that later on when you take some chemistry. But those orbitals have to have 2 electrons apiece. You can see here that there's the 4 orbitals, but each is missing an electron. So carbon has a tendency to want to make bonds. It doesn't want to lose 4 electrons. It doesn't ionize and lose 4 electrons, and it typically doesn't ionize and gain 4 electrons. It wants to share. So it has this strong tendency towards sharing. And here we have oxygen, and oxygen is going to share one of its electrons. So the lighter colored one is the oxygen's electron, and the darker colored one is the carbon's. This is just an artist's idea of what it should look like. So here we have the sharing of a pair of electrons and a sharing of a pair of electrons. Each one of these is representing a covalent bond. The sharing of electrons, or sharing of electrons in a valence shell. So remember, covalent. So this little symbol here represents a pair of shared electrons. And this one over here also represents a pair of shared electrons. So it's sharing electrons with the chemical over here, or the oxygen over here, and sharing electrons with the oxygen over here. But it produces 4. Carbon has a tendency to produce 4 bonds. Nitrogen, on the other hand, you see here nitrogen in nitric oxide is sharing 2 pairs of electrons with this oxygen atom. Okay, those are 2 examples of compounds. Different elements. Now, not all molecules are compounds, and not all compounds are molecules. Here we have an example of 2 molecules, a molecule of hydrogen and a molecule of oxygen, each of which is not a compound because we don't have 2 different elements. These are what we call diatomic molecules. Below you see hydrogen and oxygen. When they get together, they form a very special molecule and compound called water. So here we have 2 different elements, the hydrogen and the oxygen, making it a compound, and they're covalently bonded together, a shared pair of electrons here and a shared pair of electrons here. That makes it a molecule. Here I want to point out that single little line there represents a covalent bond. Up here we have a double covalent bond. Here we have a single covalent bond. So keep those in mind when you see those little lines. They're talking about a covalent bond. Not all compounds are molecules. We already talked about this a little bit earlier when we were talking about ions. Here we have NaCl. This is an ionic compound. The bonds between the sodium and the chlorine is not a covalent bond. They're not sharing electrons. Sodium has completely lost an electron, and chlorine has gained an electron, but they're not sharing them. They're not spending time around both of those elements. So by that definition, sodium chloride is a compound, but not a molecule. You cannot have a molecule of sodium chloride. You can have a crystal, and it forms into a solid mass, and that's what you find in your salt shaker. Here we have the last definition, which is the definition of an isotope. Isotopes of a specific element vary by the number of neutrons found in their nuclei. The mass number varies. And remember, the mass is protons plus neutrons. The atomic number stays the same because remember, if you change the number of protons, you change the element. And the chemical reactivity stays the same because the number of electrons does not change. So the only thing that varies is this piece here. So if protons can't change and electrons can't change, that means the only thing left to change is right there, the neutron, or number of neutrons. Over here we see hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1, you see, has no neutrons. Hydrogen 2 has a single neutron, and hydrogen 3 has 2 neutrons. Notice 1 represents the atomic mass, 1 proton. 2 represents 1, 2. 1 for the proton, 1 for the neutron. Again, atomic mass. Hydrogen 3 is 1, 2, 3. The atomic mass is 3. Now the importance of isotopes has to do with this concept of radiation. You may have heard of that term before. Isotopes can emit subatomic particles. As this changes, this neutron may degrade, and that releases subatomic particles, and those subatomic particles are radiation. Strong radioactive isotopes can cause damage to tissue. You've heard of radiation poisoning. Things like uranium and plutonium are types of radioactive isotopes that produce radiation. Weak radioactive isotopes can be used in diagnostic testing in the laboratory. You've probably heard of the use of barium in tracking changes within the gastrointestinal region. We will talk more about the uses of radioactive isotopes in diagnoses later on in the semester. Please review these terms in your textbook, in the glossary, and in the chapter. We will be using them as we further study chemistry and its involvement in anatomy and physiology.